Okay, so I'm with another video with you here. So today we're going to be discussing the glucose. The slide that you can see in here is what we learned in the previous lesson. So yeah, let's just get into the lesson. So glucose. Glucose is basically a compound that you're very familiar with. I'll just write its chemical formula with you. So it's sorry, the highlighter was not supposed to be here. So let's see. Wait. Yeah. So you can see the formula in here. C6H12O6. I'm sorry, this is not readable. So yeah, this is glucose, and it has yeah it has an aldehyde functional group, while the fructose has the ketonic functional group. Okay, wait a second. Yeah. So it's found in ripe fruits, in the corn syrup, honey, and abundant in grapes, figs, and dates. That these are basically the sources. And in our blood, the normal blood sugar will be 0.08% in combined form, and is found in many disaccharides and polysaccharides. So disaccharides and polysaccharides are what we're going to be discussing, uh, like in next lessons. Stay tuned. Okay. So it's naturally produced in the green plants through photosynthesis. For the synthesis of 10 gram of glucose, 717.6 kilocalories of solar energy is used. That's a big amount of solar energy that's used to prepare just 10 grams of glucose. So which means it can give you like this amount of energy when it's broken down, right? So glucose is stored in molecules as chemical energy and is available in all organisms when we oxidize it in our body. How do we oxidize glucose in our body? That's through respiration. The process of respiration, the slow burning of glucose. Like we just add oxygen. That's why we breathe. Okay? Why do we need to breathe? We need to breathe because we need to oxidize the glucose in our body and produce energy for us to be able to move, to be able to conduct our basic life activities. Okay, so next thing that we have is fructose. It's most abundant in nature, and it's also known as the fruit sugar. And there's galactose. Galactose is basically found in the milk. It's a disaccharide. Okay. So, what's the chemical structures of monosaccharides? So, they are usually found as open chain structures, like crystalline structures, and they are dissolvable in water. They can like solve themselves in water, and they convert to ring structure. Okay, I'm going to be showing you a little diagram about it later. Okay, so ribose, it exists in an open chain structure in dried form and in a ring structure when in aqueous form. So when it dissolves in water, the aldehyde group's oxygen would react with the second last carbon and form a link between the carbon 1 and carbon 4. Okay, and the OH group, the hydroxyl group of the fourth carbon would shift to the first carbon. I'll show you a diagram. So this is the acyclic ribose, which is a straight structure, and you can see the first carbon has double bonded oxygen with it, and yeah, that's an aldehyde. Okay, so it's got a double bonded oxygen with it. So when the oxygen's one bond number, like oxygen's two bonds, right? So one bond would just go to the second last carbon, which is carbon number 4. I'll highlight it for you. Look at this, okay? This is the first carbon, and this is the fourth carbon. And there are two bonds, okay? So one bond will just go to the carbon fourth, okay? And when the one bond goes to the carbon fourth, this ring structure forms right here. Okay, you can see this ring structure. This is the fifth carbon. This poor guy is just excluded from the ring. Okay, yeah, that's how you form a ring structure of ribose, and it dissolves in water. Okay, next step we've got more chemical structures of monosaccharides. So pentoses and hexoses and ring structure would either exist as alpha or beta bond, which depends on the position of hydrogen and oxygen on carbon number 1. And you can see in here, this is ribose, okay? But what kind of ribose is it? What kind of pentose is it? It's got the OH group is downward, which means it's an alpha sugar. In this one, the OH group is upwards. Oh, sorry, both have downward OH group. I am kind of sorry. Yeah, so if it had the OH group on this side, it will be a beta structure. Okay, so I'm sure there's another image, or I'll just draw it for you. Yeah, I'll just draw it for you. Okay, so here's a rough structure. I've not drawn the full thing, but just to give you an idea, this corner is carbon number 1, and then we go to this corner is carbon number 2, carbon number 3, carbon number 4, and I forgot to make the carbon number 5, which is just sticking out like this. Okay, so uh, this is the carbon number 5. Okay, so attached to the carbon number 1, there's an OH group and an H group. You see the OH group in here and the H group in here. So the OH group is upwards and the H group is downwards, which means it's a beta structure. Is that clear? If it's not clear, please do ask me questions. I've given you the email address and the Instagram account. You can always directly text me through Instagram, okay? Or you can just email me. Next up, I've got like more chemical structures. So ribose and glucose in water would form ring structures. Monosaccharides are crystalline powders. Tetroses are some rare things in nature, and they occur in some bacteria. The pentoses and hexoses are most common. The riboses form like 5-cornered rings known as ribofuranols, whereas glucose would form 6-cornered rings known as glycopyranols. Okay, so I added some information for you guys to see. It's related to stereoisomerism and optical isomerism. Uh, I guess the video is getting too long. No, I just continue. Okay, so stereoisomerism and optical isomerism. The stereoisomerism has the atoms making so that the isomers join them in the same order, but they still manage to have a spatial arrangement. And in optical isomerism, the stereoisomerism, it's also kind of stereoisomerism, where the optical isomers are two compounds containing the same number and the kind of atoms, but they are bounded in different spatial arrangements of atoms, and there are non-superimposable mirror images. Like your hands, you can put one hand on the other, it's not superimposable on one another. Okay, so yeah. Yeah, so the example of the stereoisomerism is like glucose. You can see the stereoisomers are the molecules that have the same molecular formula, but they differ only in how atoms are arranged in two-dimensional space. So enantiomers are the type of stereoisomers in which the molecules are non-superimposable mirror images, like I told you about your hand. This means that the molecules are mirror images, but they cannot be placed on top of one another to give the same molecule. One example of an enantiomer would be uh, dextrorotatory and levorotatory glucose. I'll draw it for you. And dextrorotatory are the right-handed and levorotatory are the left-hand molecules. So when we talk about the optical isomers like dextro and levorotatory isomers, they are basically the isomers that would bend the light in a direction, a particular direction. Okay, so if Okay, yeah. So the dextrorotatory molecules would rotate the plane polarized light towards the right, and the levorotatory would turn the or rotate the plane polarized light towards the left. Okay, so I'm going to be drawing some structures just so you can see them and differentiate between the enantiomers of glucose. Okay, forgive me for the bad drawing skills, but that's basically the level rotatory molecule of glucose, which would rotate the plane polarized light towards the left. And if I just mirror this to the just this thing will go into here, and this oxygen will go into here, and just like that, it will be basically the dextrorotatory. I'll draw that too for you, okay, just to get you proper understanding. Okay, so yeah, this doesn't look so great. Okay, so this thing CH2OH is now in here. Okay, so it was in this place, but now it's in this place. Okay, and this carbon, this carbon, this carbon, this carbon, they're basically like same kind of thing. Yeah, they were kind of same. So it's just this when you flip it, just flip it, like when you put your hand over your hand, like left hand over the right hand, while tracing upwards, then you can see that yeah, you're just yeah, that's how you make a mirror image. Okay, so that's stereoisomerism glucose. So the levorotatory, the left-handed sugars are laboratory manufactured. On the other hand, the naturally occurring sugars are the D sugars, the one that I've drawn on the right side. Okay, this one. Okay, this is a D sugar, D, and this one is an L sugar, a levorotatory. And this one is this one is a dextrorotatory, D for dextro and D for uh, yeah, dextrorotatory, and L for levo and L for left. So L for left, which means the other should be the right. Yeah. So yeah, the proteins and the cell receptors are designed to react only with the dextrorotatory sugars. For example, the enzymes in our body can digest only the right-handed sugars. Right-handed, which means dextrorotatory sugars. Likewise, metabolized by the right-handed enzymes. Just as the glove fits only on the proper hand, a right-handed enzyme cannot fit on a or react with a left-handed substrate. The substrate must fit on the proper active side of the enzyme for the left-handed substrate. Okay, the enzyme must be left-handed. So you can see how we can like make a sugar which is like you cannot digest. because it's a left-handed sugar and your enzymes are all right-handed. Okay, yeah. So there are some examples and functions of monosaccharides. The first one is a triose, which means it has three carbon atoms. You can see C3 at 603. Its aldehyde form would be an aldose. The ketone form would be a sorry, not aldose. That's what the aldehyde sugars are called. So it's glyceraldehyde. Okay, yeah. So the aldose form would be the glyceraldehyde, and the ketose form would be dihydro hydroxyacetone. Its function is that it's an intermediate in the synthesis or and the cellular respiration. Okay, so intermediate compounds would mean that one you start with reactants. Sorry, I should have used a pencil. So you start with one and two reactants, and then they convert to a product. Sometimes they won't convert to the product right away, and they need some thing to be in between. So intermediate basically means something that's in between. Okay, so it's an intermediate in photosynthesis and respiration. You're gonna hear this word a lot in this slide. So tetroses are the four carbon compounds, and the aldose form would be erythrose, and the ketose form would be erythrulose. And it's intermediate in bacterial photosynthesis. Yes, bacteria can conduct photosynthesis too. You're going to be discussing that in the chapter prokaryotes, which will be in here soon enough. Okay, so pentoses are the five carbon compound sugars. They are their aldoses would be ribose, deoxyribose, and the ketose would be ribulose. The aldose the aldose form, like the ribose and deoxyribose, are components of RNA and DNA respectively, while the ribulose would be an intermediate in photosynthesis. So hexoses, a six carbon compound sugars, would be glucose, galactose, fructose. Glucose and galactose have aldehydes. The ketoses are the fructoses. Okay? So glucose is a respiratory fuel, while the fructose is an intermediate in respiration, while galactose is milk sugar component. Haptoses, on the other hand, are seven carbon compound sugars. There are glucohaptoses and heptulose. I don't know how to pronounce it well, so sorry if I pronounce it wrong. So yeah, glucohaptose would have an aldehyde group, and ketose would have like acetohaptulose would have a ketone, and they are both the intermediates for photosynthesis. Okay, yeah. So that's all for today. Thank you so much for giving me time. Bye bye. Thank you so much.